Okay, thank you, Roberto, and welcome again, everybody. What I'm going to quickly, hopefully, talk about is the lessons, I will say, that we have been learning together with my research group at the Department of Civil and Environmental Engineering in Polytechnic di Milano on more than a lustrum long research on ultra-high performance concrete. And as a matter of fact, just to set the frame, we all know nowadays that we have to consider in each of our activities the Sustainable Development Goals of the United Nations. And some of them, which are these we go written here in green, but also number 7 here, are strictly related to our work, our profession as civil engineers. So I tried to set the goal. I said, which scenario? This picture, Tony, you might remember, we were together in Rio de Janeiro and Belo Horizonte in 2018 at the Ferrocement conference. We had a good time there. This is in Rio de Janeiro, the Museum of Tomorrow, Museo do Amanhã. And as a matter of fact, when I visited it on that occasion, I was really struck by this message here. Humankind has become a geological force, has become so strong that is able to shape the planet. Which way? Well, actually, more than half of the world population, and in a few years, 2/3 of it, is going to live in urban areas. This means that we are going to build new buildings, new infrastructures for transportation. And this causes problem of building, but retrofitting also infrastructures. This estimate by ASCE that traffic interruptions cost each household 4,000 euros just of money that is wasted, we don't know where. We must build new ports for freight. This is the port of Haifa in the Mediterranean. They are increasing the capacity to host freight ships up to 400 meters long. And this is a structural service scenario which is quite demanding for concrete structures. We need to protect costs from extreme climate events. And we also need to reduce our dependency from fossil fuels, which are one of the main problems for CO2 emissions. This is the survey by the European Union, and you can see that we still depend a lot on oil and also on fossil fuels, 10% on average, but in some countries quite much. So we must go higher, for example, in harvesting stronger winds with higher towers. We must go deeper in exploiting, at best, the geothermal energy and other forms of renewables. And we need concrete for this. There is no alternative at all. Probably some of you listened to our colleague, Professor Karen Scrivener, this morning, and according to her estimate and calculations, we will need to deforest an area as large as India every year if we would like to build with timber instead of concrete, which is not impossible, but then you must allow enough time for the timber to grow back and use. But this poses also the problem that we use a lot of natural resources. We need to produce a lot of cement, which emits CO2. So which are the possibilities that we have? Well, reduce the CO2 from clinker production, reduce the clinker in cement, and this is progresses that have been made by the cement industry. Our work as engineers working with materials and structures in the concrete field is to reduce cement in concrete, reduce concrete in buildings, and as academics, I will say also educate the final stakeholders in make a more efficient use and reuse of buildings. The issue is, which performance are we requiring to concrete? Well, we require surely compressive strength, and we look at the binder consumption. But the importance is also the metrics that we use. If we just look at the consumption of binder or cement per cubic meters, we will say, okay, higher performance concrete will require more cement per cubic meter, so it's less sustainable. That is not the right metric to look at. Look at the dosage per cubic meter of binder that you need to produce a unit of strength. And you can see that the higher you go, the more efficient you become in this. But the other thing is that we also require durability and resilience. And in this, I will say, our codes are still lagging behind. They are mostly prescriptive, and prescriptions based on composition is something which can jeopardize the innovation uptake by the industry and the progresses that knowledge has made. So this was the context in which we moved at the level of a European consortium of 14 partners. We got the funding from the European Union of about 5.5 million euros, and we have been working for more than 4 years trying to address this challenge These are the partners of the consortium, including academia and industries from the whole value chain of the concrete industry. I had the privilege to coordinate this, so we acted at 3 levels: product, process, and context. For product, we say, let's not speak simply about ultra-high performance. Let's put durability into the name. This is not a new material. It's simply a new way to look at what already exists. But let's try to embed durability into the design. So we started with UHPC. This was the first casting that we made. There is a Springsteen soundtrack behind. I hope you will not mind me for copyright. And which is the signature feature of this material, is that it develops a strain hardening response under tension, which makes it different from conventional concrete. We identified, obviously, the mechanical properties according to different tests, but we also wanted to promote a signature durability feature, its capacity to self-fill the cracks, mainly due to continued hydration and calcium carbonate. And you can see here some images. This crack, which was completely closed, not only the performance over time stayed constant, the material performance and the structural performance. We performed some microscopic investigation also to understand the reasons of this, and we also boosted it through the use of nanotechnology. You can see these data points here, in which we used alumina nanofibers. We were able to keep the opening of the single crack below tens of microns, which are really, really very narrow, no hamper for durability. Then we had to scale up from the lab to the construction site, not mixing 50 liters, but mixing 500 liters per batch. So there was also education of construction companies to this. And we used these materials in 5 full-scale pilots, 2 in Italy, 2 in Spain, 1 in Ireland, and we retrofitted this water tower in the island of Malta. This is one of the Italian pilots, ordinary reinforced concrete, 10 centimeter thick, precast UHPC, 3 centimeter thick. And you can see here the load validation. So when you end up with reducing cement in concrete and look at the mixed design, say with 600 kilos per cubic meter of cement, you have not reduced the cement in concrete. But if you look at the square meter of wall, you go for an ordinary concrete from 35 kilos per square meter to our solution, which is just 18 kilos per square meter. So obviously we have different solutions, different performance, different costs. The issue is that we must frame this into a life cycle perspective. This is the other way to look into that. So we developed, we embedded into structural design equations, the degradation mechanism for chlorides or sulfates, ending up to predict the evolution of any indicator of mechanical performance, could be the maximum bending moment, so on, over time. So we demonstrated the increase of service life in going from ordinary concrete to ultra-high performance concrete. We validated it through laboratory results, and these are the results of the LCA, and these are the results of the LCC. For an ordinary structure, you go for 400 millimeter thick walls to 1,000 millimeter thick walls in the case of UHPC. Construction costs remain quite the same because of the reduction of the overall volume, but with ordinary concrete, you increase maintenance because of degradation and corrosion, and with UHPC, you use much less. What happens at the end? Because if you say that a structure lasts 100 years, probably your stakeholder will say, I don't need it. In 50 years, I will abandon the site and so on. So we try to address the recyclability of this material. And we demonstrated that you can keep the mechanical performance. This is the compressive strength. You can also use, with fine crushing, this material as a partial replacement of cement and not only of aggregate. And we kept the self-healing capacity of this material as well. So just to summarize, this is a reflection. I took inspiration from this paper from the European Commission on the role of materials and on the keywords that we have to look into our profession. So ensuring higher materials durability, higher energy efficiency, higher degrees of material recycling and reuse. These are the challenges that we have also to pass to our younger colleagues to address their professional growth. I just want to thank you all for the attention, together with the colleagues from the different consortium projects I was involved with, and through which this research was done. This is the ReSHEAlience project on our last meeting. This is another European network, international training network, where we are educating and training 15 PhD students on these topics. I want to thank, these are the master students who worked with us during the past years, and obviously without them, no work could have been done. And these are my PhD students with my family, and also this is the nice part of our work. And I obviously have to thank the sponsor of this research and this project, the European projects, the companies who have worked with it, and some of the national research projects which have been recently funded. And thank you again for your attention.